Hello, good afternoon. My name is Ashok Gadgil. I am the director of the Environmental Energy Technologies Division. And I have the great honor and pleasure of making, I try to keep it very brief, but it's hard, introductions for today's distinguished speaker, Amory Lovins. I've known Amory since 1985. When I visited RMI at that time, characteristically, Amory said, I'll give you the tour of the new facility, but tell me, do you want me to speak to you in MKS units or English units? And at that time, I was visiting from India, so just being a contrarian, I said, MKS. And it was amazing. I mean, Amory did not pause for any noticeable tenth of a second in any unit conversions as he walked me through. Whether it was conductance, thermal mass, airflow rates, heat capacities, bang, bang, bang. I mean, he is extraordinarily well known as the person who is, I guess, the single most person whom you can point to have changed the thinking on energy efficiency in the United States and in the world. He's an experimental physicist, a MacArthur Fellow, widely considered as the world's leading authority on energy, a fertile innovator of integrated design of energy efficient systems. He was named in 2000 as Time Magazine's one of the heroes of the planet. That's the award he got in the year 2000. He got 1997 Heinz Award. He got the 2007 Blue Planet Prize. He's got, I don't remember how many. He's got how many PhDs? Honorary PhDs? 11 honorary PhDs.
Then again, I'm a Harvard or Oxford dropout.
He has spoken and briefed some 20 heads of different states. He's a consultant to more than a dozen Fortune 500 companies, because he's not just a leader of ideas for the scientists, but he's a leader of how to convert those scientific ideas into business practice and take them to scale and have a huge worldwide impact. So one of the great examples to me, and one of my heroes as a result of somebody who's not an ivory tower hero, but he's a hero engaged with the real world right from the start. And of course published hundreds of papers, 29 books, on and on and on. But I wouldn't want to take more time than that, since I too, like you are, I too am very eager to listen to him. So without further ado, please. And as is our usual practice, as a small memento of the visit, here is a framed poster of your talk.
Thank you. Wonderful. Thank you. Well, thank you, Ashok. And I want to dedicate this talk to the people of this lab with great gratitude for who you are and what you do. At Rocky Mountain Institute, our strategic focus is shifting the United States completely from oil and coal to efficiency and renewables by 2050. There's a peer-reviewed grand synthesis we've written called Reinventing Fire to be published this autumn, and it'll show how this ambitious transition can be led by business for profit. I'm going to give here a very quick sneak preview of how saving and displacing fossil fuels can work better and cost less than buying and burning them. Now, most analysts say that such big energy shifts need just technology and policy. But adding two even bigger plays, integrative design and business innovation, that is, new competitive strategies, new business models, can together create extraordinarily rewarding and disruptive business opportunities. I'm going to summarize how to save over $5 trillion net present value by running the officially projected 2050 economy with no oil, no coal, a third less natural gas, and incidentally no nuclear power. This will require no new inventions, no new federal taxes, subsidies, mandates, or laws, and it assumes that carbon emissions and all other externalities are worth zero, a conservatively low estimate. There are two big narratives here, oil and electricity. Oil and power stations each release more than 2/5 of U.S. fossil carbon. Nearly 3/4 of our electricity powers buildings, same fraction of our petroleum fuels transportation. The remaining electricity and oil run factories. So very efficient buildings and factories are the key to getting off oil and coal. And I'll get into those as sub-themes of the electricity story. Let me, though, first start with oil. America burns oil costing about $2 billion a day. The hidden costs paid not at the pump but through our taxes or health or security are even bigger. They include a $500 billion a year sucked out of our economy, mainly by OPEC's monopoly pricing that our oil dependence makes possible. Then we pay another $500 billion a year to sustain military forces for Persian Gulf interventions. That's about 10 times what we pay for oil from the Persian Gulf, and it rivals our entire defense expenditure at the height of the Cold War. Volatile oil prices also whipsaw the economy. For 40 years now, oil price spikes have preceded every recession, and oil is also finite. The Pentagon is preparing to need no oil, and the rest of us should too. Now, automobiles use most of our oil, so I want to explore how to make autos oil-free by 2050, saving $3.25 trillion net present value and spawning vast new industries. And the key is automotive physics. A typical mid-sized sedan loses 86% of its fuel energy en route from tank to wheels. After the minor use of accessories, only 13% moves the car, and of that, you can see that the biggest term is heating the air that the car pushes aside. Quite a lot also goes to heating the tires and road. Only the last 6% accelerates the car and then heats the brakes when you stop. But it gets worse. Only about a 20th of the mass you're accelerating is you. The rest is 2 tons of steel car. So only about a 20th of 6%, or about 0.3%, at most 0.5% of the fuel energy actually ends up moving the driver. This is not very gratifying, but it's what you get by focusing on improving the powertrain, because that's where most of the losses are. It's like somebody asked Willie Sutton, why do you rob banks? He said, because that's where the money is. Well, the industry has been improving powertrain for a century, and they're very, very good at it. But an even better approach, I think, is to start at the wheels and rigorously reduce those 3 components of tractive load, because every unit you save at the wheels saves 6 additional units you don't need to waste getting it to the wheels. So starting your leverage downstream wins 7-to-1 leverage from wheels to tank. In contrast, a more efficient powertrain has no leverage, it's just 1-to-1. Some simple comparisons, of course we've also done more elaborate ones, illustrate that there's no obvious correlation between cars' weight and their price. Plotting curb weight against sticker price of all the cars on the U.S. market shows a huge both horizontal and vertical scatter in each of 3 broad price bands. Or if you do the same plot for drag coefficient, it's the same story. You know, a Mercedes E-Class at 0.24 in the middle on the left costs the same as a Lincoln Town car at 0.37, but it's hardly a less desirable car, or the same for a Prius versus a Camaro. The most startling version of this scatter plot is for tires, because now California actually tests them and publishes the results. Thank you very much. So for one common tire size, for the same 60 bucks, you can get a tire with about 40% lower rolling resistance. Left is good there. And that saves you about 6 to 10% of the fuel at zero extra cost. And you don't need to sacrifice traction, ride, handling, or noise to do so. The fuel saving is free and uncompromised. Now, the biggest improvement in tractive load comes from reducing weight, because 2/3 of the tractive load is caused by the weight. Both the inertial and the rolling resistance term are directly proportional to the mass of the vehicle. For the past quarter century, though, epidemic obesity has made our 2-ton steel autos gain weight twice as fast as we have. But ultralight, ultra-strong materials like carbon fiber composites can make dramatic weight savings snowball and can make autos simpler and cheaper to build. At the same time, lighter, more slippery autos need less force to move them, so their propulsion system shrinks. And such vehicle fitness then makes electric autos affordable, because their batteries or fuel cells get smaller, lighter, and cheaper. Super efficient electric autos will ultimately sell for less than today's autos and cost a great deal less to drive. These innovations together can transform automakers from wringing pennies out of mature Victorian steel stamping and engine technologies to the steeply falling costs of 3 mutually reinforcing technologies: advanced materials, manufacturing to make them into structures, and electric propulsion. The result will be as game-changing as shifting from small refinements in mechanical typewriters to the dramatic Moore's Law-driven gains in computers. Computers and electronics, of course, are now our biggest industry, while typewriter makers have disappeared. So vehicle fitness opens a sound business path to save twice as much oil as we thought possible over the next 40 years, making affordable the electrification that can save the rest of the oil. China will lead all this if we don't, and leaders will beat laggards, just as Toyota's jump into hybrids 14 years ago is still challenging competitors to catch up. Only faster, because hybrids have just one learning curve, and the ultralight, ultra-slippery electrified version I've proposed has 3 learning curves, all of which strongly reinforce each other. Such breakthrough vehicles are, in fact, rapidly emerging. 2 years ago, our 5th spin-off, Bright Automotive, now partnered with General Motors, showed this 3 to 12-fold more fuel-efficient aluminum fleet van. Unlike other plug-in hybrids, though, it needs no subsidy to attract fleet buyers, because its fitness eliminated most of its costly batteries. But what if we make it even lighter? Well, back in 2000, my team and 2 European Tier 1s designed this uncompromised, safe, high-performance carbon fiber mid-size suburban assault vehicle. It saved over half the weight and nearly 3/4 of the fuel, with a 1 or 2 year payback at U.S. fuel prices at mid-volume production. 3 years ago, 4 now, Toyota's 1X concept car, it's a carbon fiber plug-in hybrid, was shown. It's as spacious as a Prius, but with half its fuel use and 1/3 of its weight. The day before it was shown, the world's biggest maker of carbon fiber, Toray, announced a $0.3 billion factory to mass-produce carbon fiber car parts for Toyota, not a phrase previously much heard in the industry, and later they added 4 more automakers to that club. This year, Volkswagen showed this 230-mile-a-gallon carbon fiber 2-seater plug-in hybrid slated for 2013 production, and so is a BMW carbon fiber all-electric sedan. Audi is aiming to beat them both by a year. By the way, carbon fiber slippery cars go really fast and they're radar stealthy. Now, aerospace, of course, uses a lot of carbon composites, but automaking needs about 3 orders of magnitude higher volume and lower cost I started to gain hope that that huge gap might be bridged when at the Lockheed Martin Skunk Works I met Dave Taggart, who had led the design of a 95% carbon advanced tactical fighter airframe that was 1/3 lighter but 2/3 cheaper because it was designed from scratch to be optimally manufacturable out of carbon. So he couldn't find a military customer for anything so radical, so he quit, and 1 bounce later I was able to hire him to lead the design of that halved-weight carbon fiber SUV you just saw. Now, that exercise showed also that integratively designed ultralight, ultra-safe autos don't need to cost more to make. The SUV's aerospace-inspired airframe, or frame, looks like an airframe. It's suspended from rings, not built up from a tub. It has just 14 parts, each made with 1 low-pressure die set, saving up to 99% of the $0.3 billion tooling cost. Each part can be lifted with 1 hand and no hoist. In fact, this biggest part on the side I can briefly lift with 1 finger. The parts then snap precisely together for bonding without the robotic body shop, and if you want, you can lay color in the mold and get rid of the paint shop as well. So there go the 2 hardest and costliest parts of making the car. And then the propulsion system is also 2/3 smaller, so it's lighter and cheaper, and together all of these savings pay for the carbon fiber, making the ultralighting roughly free. And carbon fiber itself is probably about to get a lot cheaper. New manufacturing technology from RMI's 4th spinoff or its competitor can make carbon fiber parts like this test piece tougher than titanium, makes a good carbon cap, in just 1 minute, scaling to automotive cost and speed with Aerospace Performance. If we made all U.S. cars this way, it would be like finding a Saudi Arabia under Detroit, because ultralighting saves half the weight and half the fuel. The car gets peppier but also safer because this stuff absorbs 12 times as much crash energy per kilo as steel, and yet the car costs about the same to make. Now, to achieve such big mass savings, you have to go several times around the design spiral, as it's called in naval architecture, or the design cycle, as it's called in aerospace. You start off making the vehicle as light and slippery as you can think of, so you need less power to run it. So that encourages you to use more advanced powertrain, and it gets smaller, and the brakes and suspension and so on also get smaller. That's good because that all leaves more space for crush space, because you're on the road with heavy stuff. And then you go around the spiral again and again, making things smaller, lighter, simpler, cheaper, as their structural load strength, but also often eliminating components altogether. For example, a good series hybrid, which becomes cheap with several-fold lower tractive load, can eliminate the transmission, clutch, flywheel, axles, differentials, drive shaft, U-joint, starter, alternator. That stuff just goes away, so you get jumps in mass saving, which then compound further. And at first the ultralighting might seem too costly, but as you go around this cycle a few times, you need so little carbon fiber and electric traction and storage and so on, and manufacturing the advanced composite structures can become so simple and cheap that all that pays for the carbon fiber, making the ultralighting approximately free. And that is indeed what we're finding. Now, to achieve such results, you also have to design in the future, not in the past. When the Soviets shot down Francis Gary Powers' U-2, Kelly Johnson at the Skunk Works did not say, "I'm going to design a little bit better U-2." He said, "I want to own the skies for decades. Let's do a Blackbird. I don't know how, but we'll figure out." It took him about 13 months. And Johnson understood that such an airplane was impossible within the conventional design context. He knew that design is like a rubber band. If you try to stretch it too far from the conventional design space, you encounter more and more resistance, and ultimately it breaks. So if instead you jump to the design space you really want, you can stretch the rubber band back as much as necessary for technologies that aren't mature yet, and then as they ripen, the rubber band relaxes to where you want to be. This is true not just of aircraft, but of all vehicles and indeed all kinds of design. Now, at first, when there's still a low volume, the carbon fiber electrified cars will cost more than many customers are willing to pay up front. So to reach volumes that go down those three learning curves and make the batteries and fuel cells readily affordable quickly enough to forestall a whole generation of inefficient oil-burning cars, we need a Feebate, that is, that's Art Rosenfeld's term for it, rebates for efficient new autos paid for by fees on inefficient ones. This widens the price spread within each size class enough to bridge the gap in discount rate between private buyers and society. Europe has now 4 successful Feebate programs. The biggest one in France is shown here, and in its first 2 years it tripled the rate of improvement of new auto efficiency. It nearly doubled the market share of the most efficient models and cut the share of the least efficient models by 2/3. And as you can see, it did that at both high and low oil prices. Now, autos with the tripled fitness I illustrated could adopt battery electric propulsion very rapidly, even before those 3 learning curves brought their price down enough for a payback within 2 years. This would happen by about, they'd get to the 3-year payback by about 2028, and by 2035 or thereabouts, even in the more recalcitrant vehicle categories, you could phase out the Feebates. But meanwhile, the Feebates would cover you in that red zone and continue to preserve margin and accelerate sales. By 2050, both the battery electric and the fuel cell autos should beat EIA mobiles on first cost alone. So Feebates would end up unlocking about $2.5 trillion of net present valued oil savings, rising to about $4 trillion if smart fleet purchases sped the retooling. Fleets, of course, are typically bought on a spreadsheet, not on emotion, using normal business discount rates rather than implicit consumer discount rates. So fleets could be the first adopters while Feebates are being adopted, just starting in the next few years. The result is, by the way, nearly identical, actually a little better with fuel cells as for batteries. This is the fuel cell original version of that SUV I showed earlier. Virtually all official assessments and DOE policy concluded the fuel cell autos are unrealistic. That's wrong because vehicle fitness reverses the answer. And I hope DOE realizes this before it drives the rest of this technology overseas. Now this packaging diagram of that SUV design illustrates why in fit vehicles, hydrolistic competitor, when the tractive load drops by 2/3, so does the size of the hydrogen tanks needed for a normal, in this case 330-mile driving range. They package well with no breakthrough in hydrogen storage and without needing the 700-bar tanks many people noodle about. Of course, conformal tanks would package even better, but for analytic simplicity, we use the off-the-shelf cylindrical ones. Also, the fuel cell, which is this little box, and now it would be about half that size, gets 3 times smaller, which means you can pay 3 times more per kilowatt. So at a, say, 80% experience curve, you could get to your competitive price point with about 32 times less cumulative production, and that cuts a decade or 2 off the deployment time. And the infrastructure problems were solved 12 years ago through an integrated deployment model for mobile and stationary uses. Now, the same physics and the same business logic apply also to other vehicles. If you save half the fuel of 18-wheeled trucks at a quarter the cost, that would be really valuable, but it's actually becoming a reality. We showed this several years ago. Academy found the same thing. It doesn't even look much different. The bus on the right, for example, which is about the size and shape of a truck, has half the drag coefficient of a normal truck. And 2/3 of the over-the-road load for moving a heavy truck is its air drag. The other third is rolling resistance. Walmart has actually already saved 60% of the fuel per ton mile in its truck fleet in the past 5 years. And the next step, if we can harmonize state standards, would be to raise the nominal saving from a half to 2/3 through long compound trucks, hooking 2 trailers to 1 tractor with a C-dolly hitch that does better safety and more axle increase than weight increase so that the road wear goes down. Also in the cards are doubled and tripled efficiency or better aircraft. For example, the strut-braced wing design at the upper left can triple or quadruple efficiency for a tube and wing airplane. The blended wing body design in the center can double to quadruple efficiency in military designs and maybe civilian. Honda's carbon fiber business jet saves weight and noise and fuel with an engine over wing design. A NASA truss-braced wing design here with a single buried rear propulsor is obviously extraordinarily efficient. And just for fun, on the lower left is the seed pod of the Cambodian cucumber, which can glide for hundreds of meters. That's a really good glide ratio. Maybe we can get that good. Now, meanwhile, the military, which has a life or death interest in efficient mobility, is starting to value saved fuel 1 or 2 orders of magnitude higher than previously, because they're now starting to count the fully burdened cost of the fuel delivered to the platform in the battle space. Well, this huge increase in the value of saved fuel is going to drive, starting already to drive, innovation that will then come back to the civilian sector, which burns 50-odd times more oil, and it will accelerate the kinds of platform efficiency I've described, just as past military science and technology investments have given us things that transform the civilian economy, like the internet and GPS and the jet engine and microchip industries. And indeed, we're still at an early stage of becoming as good designers as nature is. The late Paul McCready had this lovely drawing of some of the advanced aerodynamic and other innovations in a California Condor, including advanced manufacturing techniques. Maybe we'll get this good quite a while from now as we learn biomimicry. Now, as we make our vehicles technically more efficient, we design and build them better, we can also use them smarter. If this graph of weekday traffic congestion on our roads were an electricity load shape, we would throw a lot of IT and pricing at it to try to flatten it out. But by not yet doing that for road traffic, we are wasting many billions of dollars a year through idle people, idle vehicles, and idle roads. But now we know how to charge real-time driving costs per mile, not per gallon, and use smart IT to enhance transit and empower car sharing and ride sharing, and allow lucrative smart growth real estate models, so people are already pretty much where they want to be and don't need to go somewhere else, and use intelligent transportation systems to make traffic free-flowing. And together, these approaches turn out to have the proven potential to give us the same or better access with 46 to 84% less driving, saving another $0.8 trillion present value. Even more disruptive would be solutions economy business models like Zipcar that lease you a mobility or access service, in their case by the hour, instead of selling you a car. And this could boost the asset utilization of cars from 4% up to maybe an order of magnitude more. Now, if you put all these things together, then 40 years hence, 36% more Americans can enjoy the enhanced mobility of a 100% bigger economy, 150% bigger economy, and yet use no oil, and you save $4 trillion net present value, including the fuel infrastructure bought or avoided. Those 125 to 240 mile a gallon autos, by the way, can use any desired mixture, and there will be vibrant competition here, of hydrogen, electricity, and advanced biofuels. I don't much care which, and nobody can know which. Trucks and airplanes can realistically use advanced biofuel. Trucks could optionally use compressed natural gas, because that packages well when the trucks get efficient. Any biofuels we might need could be made without displacing cropland or harming climate or soil fertility, because it's a small number. This totals only under 3 million barrels a day. Now, my team speeds these kinds of oil savings by what we call institutional acupuncture, seeing where the business logic is congested and not flowing properly and sticking little needles in it to get it flowing. Our partners in this range from Ford to Walmart to the Pentagon. I think most of the 6 sectors that need to be transformed to get us off oil are already at or past the tipping point where this long work starts to get easier. Boeing, for example, already converted its Dreamliner's leapfrog efficiency into a powerful competitive strategy, and now Boeing Commercial Airplanes' former CEO has led Ford to become a top lightweighter and the world's second most profitable automaker. In 2009, mainstream analysts even started to see peak oil not in supply but in demand. ExxonMobil agreed U.S. gasoline use had peaked in '07 and will never increase again. Dan Yergin said all industrialized countries' total oil use had peaked in '05 and will only decline. And Deutsche Bank forecast world oil use will peak in about another 5 years, and then by 2030 fall to about 8% below today's value. That's just based, by the way, on electrification of light-duty vehicles, and in China they assumed a third the rate that China's actually targeted. So in short, oil is already becoming uncompetitive even at low prices before it becomes unavailable even at high prices. Now, less than 1% of our oil, but 95% of our coal makes electricity. So our second big story is about saving electricity, then making it differently. These twin revolutions promise more numerous, diverse, and profound disruptions in electricity than in any other sector. It's going to be a challenging transition because you've got 21st century technology and speed colliding with 20th and 19th century institutions and cultures to create the most perilous and rewarding transformation inflection point since the internet. Today, most of our electricity is wasted, and efficiency technologies, thanks to many of you, keep improving faster than they're applied, so the efficiency potential keeps getting bigger and cheaper. Over the next 40 years, smarter building technologies and operations can save about half the electricity and gas used in our buildings, worth over $1.4 trillion net present value. Implementation needs systematic barrier busting, mature delivery by well-trained people, and owners paying attention. But there's an even more disruptive innovation, not, I think, much in your studies yet, that can boost that energy saving to well over 70%. It's called Integrative Design, and it can often make very large energy savings cost less than small or no savings, turning diminishing returns into expanding returns. For example, my 1984 house at 7,100 feet, 2,200 meters elevation, it helped inspire 25,000 now European buildings that need no heating but cost about the same to build. Ours also has no heating or cooling equipment down to minus 40 odd. Of course, it doesn't have to look like this to work like this. It can look like whatever you want. Inside, we've so far harvested 35 banana crops with no furnace. In 1984, this building saved about 99% of the normal space and water heating energy and 90% of the household electricity, all with a 10-month payback. If you look, you don't have great resolution, but there are dark green objects in here. Those are some rather large papayas as of a few weeks ago. Now, today's technologies, which we just retrofitted, are even better. I can't yet tell you how much better because we're still commissioning the software to display the 250 data streams we're monitoring, but it does appear that the monitoring equipment is using more electricity than the lights and appliances. Now, this design approach works in any climate, including eliminating air conditioning up to 115 F46C with lower construction cost and better comfort. The key is integrative design that gives multiple benefits from single expenditures. For example, the white arch up there has 12 functions but only one cost. There's hardly any component in the building with fewer than 3 functions. 6 or 8 is more normal. And this approach also works for big buildings, old and new. Last year's retrofit of the Empire State Building is expected to save 38% of its energy. Remanufacturing its 6,500 windows on site into super windows, thank you, Berkeley Lab, that are almost perfect in letting in light without heat, plus better lights and plug loads cut the peak cooling load by a third. Then instead of having to close and dig up Fifth Avenue to replace and expand the chillers, we were able to renovate them in place and reduce them, saving $17 million of capital cost that then helped pay for the other improvements, and that's what cut the payback to 3 years. Similarly, retrofitting a 20-year-old curtain wall office building near Chicago, we found, could save 3/4 of its energy at slightly lower cost than the regular 20-year renovation that saves nothing. So why isn't this approach more widespread? Well, just because we're all taught about the law of diminishing returns, saying that, in conventional practice, the more you save, the more it costs. There is no such law, and if there is, I break it all the time. Economists think this is impossible. Often the engineers think it's fun. But in conventional thinking, you invest in efficiency, like, say, adding insulation only till it's not worthwhile anymore, and then you stop at this cost-effectiveness limit. But if you keep investing in even more efficiency, like the double insulation in my house, you get to the point where you no longer need the furnace, ducts, fans, pipes, pumps, wires, controls, fuel supply arrangements, and you end up with a capital cost lower than you started with. So optimizing the building as a system, not the insulation as a component, yields expanding returns. And such integrative design is the next revolution that I hope this lab will help DOE and others to apply throughout analysis programs and policies. This means getting rid of our metal silos so we optimize the whole building for multiple benefits, not isolated components for single benefits. In my house, for example, I didn't start by asking, as most engineers would, how much insulation can I add and still save enough heating fuel to pay for it? That's methodologically wrong because it leaves out the capital cost of the heating equipment. Rather, I asked what integrated combination of insulation and many other technologies could save occupants the most energy cost, capital cost, discomfort, illness, and dismay. So I got a house that creates delight when entered, pleasure and health when occupied, regret when departed. A house that takes nothing, wastes nothing, does no harm, and saves enough energy to pay for the whole house over a few decades. The key to achieving that at lower capital cost was choosing expensive glazings. Now, in summary, our buildings analysis in Reinventing Fire starts with an EIA base case, which we extrapolated from 2035 to 2050. It backs out the savings baked into the EIA forecast to get a business-as-usual future. And then we use basically the Academy analysis of savings plus some further smart control stuff that's been demonstrated. And then we picked a range of possible values for integrative design, and we ended up, as you see, with not very much left. And the marginal costs of the integrative design would range from significant but worthwhile to zero or less, depending on the quality of design and execution. And that last step would require overhauling design practice and pedagogy. So we have a plot for the nonviolent overthrow of bad engineering called 10xe, Factor 10 Engineering. And if you go to 10xe.org, there are related papers on the right. The first two are my latest summary of how to do this. Or if you go to rmi.org/Stanford, you'll find my Stanford Engineering School lectures of 4 years ago going into some more detail. Now, if you combine all of these savings at realistic implementation rates, you end up saving about 53 to 70% of the building energy below EIA projection, or about 40 to 60% below today's level, and with major financial and health and other, like productivity, benefits for owners and occupants. And the gross energy savings are worth $1.8 trillion net present value, of which the cost is 0.4, so the net is 1.4. As you can see, our findings make yours look terribly reasonable. I hope you don't mind. Now, in industry, the same approach can further increase the $500 billion of low-hanging efficiency fruit that's already fallen down and is mushing up around the ankles and spilling in over the tops of our waders. For example, 3/5 of the world's electricity runs motors, half of that runs pumps and fans. And there are about 35 things you can do to a motor system to save about half the motor system energy from the electric input to the input shaft of the driven machine, with about a 1-year payback, because you only pay for 7 of the improvements. The other 28 are free byproducts. But first, we ought to stop wasting most of the energy used by the equipment the motors are driving. For example, pumps, the biggest use of motors, move liquids through pipes. The Dutch colleague redesigned a typical industrial pumping loop to use at least 86% less pumping energy and cost less to build, just by replacing long, thin, crooked pipes with fat, short, straight pipes. That's how this recent design of Eng Lok Lee in Singapore saved 69% of normal pumping energy at lower capital cost. In fact, in my own house, we just retrofitted some hydronic plumbing, and I think we saved about 97% of the friction at lower capital cost just by using fat, short, straight pipes. Now, what does such savings mean for the electricity that is 60% used in motors? Well, from the coal burned at the power plant to the end use, there are so many successive losses compounding that only 1/10 of the input fuel energy comes out the pipe as flow. So now turn those compounding losses around backwards into compounding savings from right to left, and every unit of flow or friction you save in the pipes saves 10 units of coal and cost and emissions and global weirding back at the power plant. And also, as you go back upstream, each component gets progressively smaller, therefore cheaper, so you save the most capex as well. My team has lately found such snowballing energy savings in over $30 billion worth of industrial redesigns, from data centers and chip fabs to mines and refineries. Typically, our retrofit designs save about 30 to 60% of the energy with a 2 or 3 year payback. In new installations, we do better, typically 40 to 90%, and the capital cost almost always goes down. And that, I think, is a missing dimension of the federal studies we see so far. Let me give you an example from a recently completed data center. If you start, just like the pumping diagram, feeding 100 units of fuel into a power plant, maybe 30 will get to your meter. And half of that won't get to the servers because it's used first in the uninterruptible power supplies and the cooling that are half your capex. And then of what gets to the servers, only about half gets to the chips because of terrible power supplies and lots of fans taking heat that shouldn't be there off the motherboard into the room so we can do dumb things with it. And then, of course, most of what the chips do is wasted as well because of severe underutilization of all computing resources. Now, this is getting so small, I'm going to have to magnify it before it disappears. Then the next problem is bloatware. So a lot of what the chips are doing that are computing is running threads and processes you didn't really want or need. And after that, you might even have inefficient business processes downstream. So very, very little of the energy, maybe 3 orders of magnitude down, actually creates customer value. So as usual, we start our savings downstream. The first thing we would do is write terse code elegantly compiled and accelerated so that every compute cycle is a needed and wanted one. Then we would buy servers about 4 times as efficient at the same cost, maybe less because there's less to them. Then they need, of course, a lot less cooling and power supply, and there are much smarter ways to do that than the usual ones. And if you wanted, you could even get rid of half the utility loss with on-site fuel cell trigeneration. And when you multiply all that, there's 2 orders of magnitude or more leverage in energy savings. I think our last design, had they fully executed, it would have been a 95% saving on energy and half the capex gone as well. So our industrial analysis has the same kinds of structure as the building analysis. It has both the structural or compositional and the efficiency savings that are baked into EIA. We get rid of the refining that's no longer required to make the fuel the transport sector no longer needs, and then we add back what the advanced biofuels and hydrogen might use to create. We take the lab reports on emerging efficiency technologies and also make sure that the cogen and waste heat recovery are fully counted. And then we had a very conservative allowance for integrative design. We counted it only in the missing bits of drive power and in fluid handling friction reduction, but we don't count it anywhere else, and I think that's going to prove a very conservative number. At any rate, we end up excluding feedstocks. This is only about combustion, with a very large saving, and the implementation similarly requires systematic barrier busting, mature delivery, owners paying attention. Not easy, but the prize richly justifies the effort. Now, meanwhile, how the world produces electricity is shifting dramatically, accelerated by efficiency and hence falling electricity use. Already, as you can see from these annual additions, wind and photovoltaic additions are growing explosively, while the orders for central stations wither because they have too much cost and financial risk to attract investors. This renewable power revolution, the biggest infrastructure shift in history, is led by China, which is #1 in 5 renewables and aims to be in all. I was just running the numbers the other day. Portugal, by the way, has just increased its renewable share of electricity in the last 5 years from 17 to 45%, while the U.S. went from 9.2 to 10.5. Power sources that get their economies from mass production rather than from big units have more than swapped their share of global electric generation in the past decade with nuclear. In fact, in OD 8, the last full data we have, micropower was actually about 91% of the world's new electricity that year, and renewables added half the world's new generating capacity. So this is not a fringe activity. It's actually taking over the market. Last year alone, renewables, except big hydro, got $151 billion of private investment. They added 52 gigawatts of capacity, and they surpassed nuclear power's total global installed capacity. New U.S. nuclear plants, if any, are upwards of 100% subsidized, but they can't raise any private capital because they have no business case. So without that, how could you displace the coal-fired nearly half of our electricity, which I'll show here as a magenta line on this horizontal scale? That's the finish line we have to get across. Well, the first thing you'd want to do is things that cost less than running an old coal plant. And you could get rid of about 65% of the coal-fired electricity if our country were as productive in using electricity as the top 10 states were five or 6 years ago, adjusting for each state's economic mix and climate. Even more, of course, could be profitably saved. And then secondly, it is now generally cheaper to run coal plants less and existing combined cycle gas plants more, because the merit order has flipped, and that will save about 35% of our coal-fired electricity. So 65 plus 35 is 100. We're already there. We can displace all the existing coal plants without any substitute supply construction, and cheaper than running the coal plants. Now, next would come options cheaper than building and running new coal plants. Wind power now stuck in the queue awaiting grid interconnection, 300 gigawatts or so, could displace about 2/5 of the coal power. All the profitable wind power on available land could displace coal power 19 times over. Cogen in industry and big buildings could displace about 2/3 of the coal power, plus more in smaller buildings, plus other renewables we haven't even evaluated yet. But then there's another category, which is options that cost more today in engineering economics terms than a new coal plant, but wouldn't by the time you could build the coal plant. Photovoltaics are in that category, and if you put them on about 3% of our structures, that's enough to displace all the annual coal-fired electricity using no land. So you add all this up, and we now have profitable non-nuclear ways to displace coal power more than 23 times over, or if you wish, coal and nuclear 16 times over. You only need to do it once. So, but we're often told that only the coal and nuclear plants can keep the lights on because they're 24/7, while wind power and photovoltaics are variable and hence, we are told, unreliable. Well, actually, no generator is 24/7. There is no such animal. They all break. Coal and nuclear plants fail about 10 to 14% of the time, losing a gigawatt in milliseconds, often for weeks or months and without warning. Now, grids routinely handle that intermittence by backing up failed plants with working plants, and they can handle solar and wind variability, which is forecastable, in just the same way. So my team's been doing hourly simulations, and we found that very large renewable fractions can deliver highly reliable power when forecasted, integrated, and diversified by both type and location. For example, if the normal Texas daily load shape in the summer, the ERCOT power pool, is cut down and made less peaky by efficiency. And then we can install wind in green and photovoltaics in yellow, but they won't exactly match the load. However, flexible demand and smart charging and discharging of electrified autos can mesh all the moving parts, even with 86%, in this case, variable renewables. The other 14% or less, which is shown in aqua, you see it's not much area, can come from dispatchable renewables like geothermal, which we have down at the bottom, small hydro, solar thermal electric, feedlot biogas burned in existing gas turbines. So, and some utilities, of course, already integrate variable renewables in this way. That's how 4 German states last year got 43 to 52% of all their electricity from wind. Now, one of the important resources in making all this fit together is demand response. This is how we saw it in buildings in different end uses in ERCOT, using only unobtrusive measures. But the total is several times bigger than had been thought when people didn't look in such a fine-grained fashion. And in the dispatch example I just showed you, we only counted ice storage on air conditioning. We didn't count the rest, maybe the other 2/3 of the demand response resource. So that 86% will actually go up when we do. And of course, treating demand not as simply assumed, but as something that customers and utilities can substantially influence or change, adds valuable flexibility to a grid that's shifting to variable renewables and without customers noticing any of this. They'll just save money. Now, Reinventing Fire explores 4 electricity futures, 4 scenarios that don't differ much in cost. The little red box in the upper right, that's the present valued cost of electricity over the next 40 years. But they differ greatly in risk. This is the business as usual future, which has high financial, fuel, and climate risks, and its over-centralized grid is vulnerable to cascading and potentially nation-shattering blackouts caused by bad space weather, geomagnetic storms, or by terrorist attack. Now let's change the 3 big components here, nuclear, coal, and gas in pink. So another way you could meet the same demands but hedging climate risks would be to add new nuclear build and so-called clean coal. That turns out to cost about $1 trillion more. It intensifies the technical and financial risks. It retains all the other risks. Or you could get climate-safe power without that extra $1 trillion cost by quintupling today's utility-scale renewable capacity so it meets 80 or 90% of our needs, ultimately 100. And this centralized renewables scenario would sustain or improve reliability. It would cut technology risk, somewhat reduce financial risk. It would reduce blackouts. And then finally, if we let distributed generators compete fairly with centralized ones, that would nearly eliminate the grave blackout risk by organizing the grid into netted islandable microgrids that can stand a load at need. That resilient future would cost about the same as business as usual, but would manage all of its risks and would maximize customer choice, entrepreneurial opportunity, and innovation. I think it's a much better fit to global trends. It does require difficult regulatory reforms, barrier busting for efficient use, a smart grid, maybe adding transmission, though probably a lot less than we thought, purging obstacles to fair competition and fair interconnection, and public policy could speed or slow these quite powerful market trends. Just a few broad observations on the preliminary comparisons here. The renewables, case 3 and 4, need more capacity for the same output, but there are many choices of output, especially if the learning curves, as in case 4, ultimately make photovoltaics even cheaper than wind. Renewables will save, as you can see at the right, about $1 trillion worth of, down at the bottom here, about $1 trillion worth of fuel, which is this brown part. So the renewable scenarios pay a lot less in fuel than the non-renewable ones, and then you put that back into capital cost, and that offsets or more of the extra generating capital cost. The added transmission cost down at the bottom, that's this little wedge here, is surprisingly small and probably gets even smaller as we properly compete transmission with the mixture of efficiency, demand response, and distributed generation. And it's actually the same in cases 1 and 4, more or less. And the total cost is remarkably similar for cases 1, 3, and 4, well within analytic uncertainty. So the choice should be based on relative risks, not relative costs. So our book goes into quite a lot of detail on that. Now, together, these transformations in efficient use and diverse dispersed renewable supply are starting to flip the whole electricity on its sector on its head, from this familiar model to an upside-down one. And this, it appears, is not going to need much, if any, bulk electricity storage. Although you may have noticed in the Texas case, we did use plug-in hybrids vehicles as distributed storage. These best buys are, of course, coming in faster where utilities are paid for cutting your bill rather than selling you more electricity. And these are also the best, most effective solutions to climate change, nuclear proliferation, energy insecurity, and energy poverty. And this approach, I think, is highly fungible. The technologies are certainly fungible, and how you put them together and what sorts of policy you use are adaptable or adoptable. A third of the gas and all of the nuclear, coal, and oil. That is motivated by profit. It is supported by civil society and mindful markets. It's enabled and sped by smart policies. And efficient use of energy in the 3 use sectors, smarter use of energy services, fuel switching, can save, it turns out, over $6 trillion net present value, counting no externalities. While an electricity sector that resolves today's serious security, financial, and climate risks increases cost by less than $0.4 trillion, if at all. So that's where you get the $5+ trillion net prize, and business can compete for that. Our energy future, then, is very flexible. It's not fate but choice. That choice is very much in the hands of the people in this room. And I think to get this job done, we're going to need to do some pretty hard things outside this room, reforming the auto, truck, and airplane industries. Fortunately, competitive forces will help. We'll need unprecedented progress in getting better access with less driving. Again, strong real estate value trends will help, but it won't be easy to desubsidize and demandate sprawl. That's why we have so much of it. We're going to need to roll out efficient buildings and factories on a tremendous scale and continue down aggressive renewable energy cost curves. Again, markets and we as Americans are good at these things. We're going to need to revamp utilities' regulatory and operating models and probably some of the rules that influence building and factory owners. We haven't been so good at those kinds of changes, and we better get good at it quickly, because waste is a terrible thing to waste. The rich synthesis that I briefly sketched here is not just a book. It drives Rocky Mountain Institute's portfolio of sectoral implementation initiatives. 4 of those are already underway in deep retrofit of commercial buildings. Look up our retrofit depot on the web. Super efficient but same cost new production housing, next generation electric utilities, and factor 10 engineering, 10xe, for radical efficiency in industry and indeed in all sectors. We've spun off a 5th initiative in heavy trucks to the roughly 300-firm North American Council for Freight Efficiency that we helped set up. We're exploring an initiative in civil and military fleet vehicles, supported by our Project Get Ready, which is speeding deployment of electric vehicle infrastructure in over 15 cities. So what you've heard here rests on very detailed practical experience and empirical evidence. I think it reflects where the smart companies are headed. Of course, they're not the only ones out there. As Oilman Marie Strong said, not all the fossils are in the fuel. But as DuPont's former chair, Ed Woolard, said in another context, firms hampered by old thinking won't be a problem in the long run because they won't be around. And if you think anything I've said here sounds too good to be true, just remember that nice saying of Marshall McLuhan that only puny secrets need protection. Big discoveries are protected by public incredulity. So I hope that you will become more engaged with our work and we with yours in making the world richer, cooler, fairer, and safer by together reinventing fire. Thank you for your good work and your kind attention. I'm sure I said nothing controversial, but...
Since it is past 1 o'clock, I want to take this time to say officially the meeting is over, but we have time for questions. So those of you who need to leave, feel free to do so.
Hi. What do you see? You know, you've always had a very practical-based business model view of how these things should be implemented as opposed to, as you say, regulatory policy top-down view. What are the major obstacles that you find in reality to accepting those principles and implementing them? Of course, you've got very practical things. I own 10,000 to the Empire State Building, so I know about that little part. And there seems to be a lot of acceptance starting in different industries to actually attempt these. So, but what are the biggest obstacles that you find?
Well, they're, of course, different by sector. In the auto industry, the main barriers have been cultural within the automakers, not so much in the tiers, the suppliers. And this, I've been a cultural repairman in Detroit now for 20 years, and it's rather unusual. They have some behaviors I haven't seen in 29 other sectors, like, let's see, counting cost by the part or by the pound, as if you bought a car that way. Actually, of course, you buy it by the car. So they tend not to see very readily, this is starting to change a bit, that if you spend more on the body in black, you can spend less on other stuff and it works out the same, only your margin goes up. And they also tend to treat sunk costs as unamortized assets, that is, to base strategic decisions on accounting, not economics, as if it were better to write off obsolete stuff later when you don't have a company than now when you do. So 2 of them just had to do that. I think competitive forces are starting to sort those out. You know, near-death experience does concentrate the mind wonderfully. But still, the cultural change is hard. In buildings, it's much more complicated. We're all familiar with stuff like split incentives and lacking information and so on. But really, I started to dig into this in '92, and I realized that the U.S. had misallocated $1 trillion of capital by then to 200 million tons of HVAC equipment and 200 peak gigawatts of power supplies to run it that we wouldn't have built in the first place if we'd optimally designed the buildings to produce optimal comfort at least cost. And then I realized that in, say, the commercial value chain, commercial real estate, there are about 24 parties, each with stunning perfection, rewarded for inefficiency and penalized for efficiency. If you were to try to design a set of relationships and rewards and habits that would make our buildings use an order of magnitude more energy than they should, cost more to build than they should, and be less comfortable, healthful, and productive to be in than they should be, you'd be really hard-pressed to improve on the system we've got. Very little of it is regulatory. I mean, for example, we pay our architects and engineers for what they spend, not what they save. So we did 5 experiments with performance-based design fees, which turned out to have a very salutary effect on design, and now need some big clients to insist design be bid that way, and big design providers who want to distinguish themselves in a crowded market by saying, let us bid that way. And it's those other guys that don't want to take the risk because they know they're not very good. But each of these 24 perverse incentives can be a showstopper, and yet each is a business opportunity, and you only get the opportunity if you can deal with all of them. That's what makes it complex. In the utility sector, there's a whole other set of things around, insisting on electricity only, prohibiting cogen, not allowing fair competition and hookups, not fairly comparing the attributes of different assets, and so on. And the biggest one, of course, is that 40 states still reward utilities for selling you more electricity and penalize them for cutting your bill. That's just as dumb as it sounds, and we need to stop doing it. This state does not have that problem. Sir?
What's T. Boone Pickens' current status in the wind?
What is what?
T. Boone Pickens hadn't put a large investment into the wind industry, and then he stopped?
He stopped, I believe, because the gas prices plummeted and because he couldn't get somebody else to pay for the transmission lines. But I expect that will come back. He has a very good West Texas wind resource. I think he laid off the turbines on some other buyer for the moment, and the lines are being built. He was a few years ahead of those. No, Boone's a good businessman. He'll figure it out. Notice that, let's see, are Ryan Weiser and Mark Mulger here? No? But the folks here have worked out that it's worth paying a cent or two a kilowatt hour, maybe even 3 extra for wind power, because it's a free gas price hedge. It isn't just a kilowatt hour commodity. It has no fuel price risk. And similarly, one of my trustees, who's a financial wizard, just looked up in Bloomberg and got the straddle price for selling a put and a call simultaneously on energy commodities. And over a 1 to 5 year time horizon, there's a $1 or $2 per MCF price premium on gas if you want to get it at a constant price and let a trader take the risk for you. Well, that means a whole lot of stuff beats gas that you might not think of if you didn't do financial economics. So when you're selling renewable or efficiency kilowatt hours, make sure you get paid for the non-volatility of their price.
Amory?
Yeah.
This has been a brilliant talk in terms of bridging technology and business. I've been personally tremendously frustrated that my institution has not allowed me to specifically invest my retirement income in forward-thinking business with respect to energy. If one place ought to be doing this, I think ours ought to. Can you give us any advice about places to look for people who are doing the kind of analysis that would provide for sound financial planning that individuals and corporations could head toward, that would help both make this transformation more possible and accessible?
Well, I can't legally give investment advice, and if I did, it would be worth what you paid for it.
No, but are there, in your opinion, any institutions that are actually starting to think about this in a serious fashion?
Yeah, there are many clean and green investment vehicles of all sizes and flavors, and if your institution doesn't let you invest in them, that's a separate problem. And I don't know how to solve that one. We have a similar conversation going on in RMI, and it's actually usually of the different form that investments in retirement funds are often confined to fairly high-load managed vehicles when you would do a lot better with a Vanguard or Fidelity no-load and not pay the fees. One diversified fund is as good as another, and you cannot actually beat the market by managing over the long run. But yeah, I think putting your money where your heart and your head are is a good thing. And if you can't do it, you got to solve that problem. But it's not for lack of vehicles to invest in, sir.
Oh, fantastic, thank you, Amory. I really love your quote that you can't optimize the system by optimizing the component, and we need to move towards systems thinking. Have you seen any of that integrated design philosophy starting to emerge for communities or cities as opposed to sectors?
And actually, the best example I've written up or know about is in Curitiba, Brazil. It's chapter 14 of our book, Natural Capitalism, with Paul Hawken, 1999. You can download it free from natcap.org or naturalcapitalism.org. And they haven't actually done a great deal yet with energy and water efficiency in Curitiba, but they've integrated in many, many other dimensions in a most impressive way. So, others have written up, like what's his name's book, Hope, Human and Wild, Bill McKibben. He wrote up the Curitiba redesign as a political phenomenon. I wrote it up as a design solution. So and it rather surprised the Curitibans because even though they'd done it, the fish doesn't know it's in the water. They didn't quite realize how they'd done the design. And that was actually a bottom-up community organizing affair, but with very astute thought leadership by Jamie Lerner, who's an architect, engineer, and others. Really a group of architects did the thought leadership and then had the savvy to organize it in such a way that it permeated the political structure and became unstoppable.
Given Amory's schedule, we have time for 3 more questions, which is a lot.
Jim?
Amory, we're a research institution. Should we conclude that all the solutions are already out there, or are there areas you would suggest that additional research would be?
Oh no, I think your research is wonderful, both in the details and in the integration it brings. And I would urge you to educate your customer about integrative design in everything that you do. I think that adds even more power to your work. I mean, when the Academy, in its big energy report a couple of years ago, mentioned integrative design for buildings for several pages, but drew no conclusions and left it out of the calcs, and then didn't even think about it for vehicles and industry, it wasn't for lack of telling them. I don't know whether it's because the economists can't get their heads around it because expanding returns makes their models blow up, which is embarrassing or inconvenient, or for some other reason. But I think this is the next big blockage we need to overcome in how we think about these problems. The research that you're doing on technology and its application is going to make everything I described easier, and indeed it's essential to the results we described, because we took your emerging technology reports and applied them as far as they went in time, and then assumed, which has good historical support, that from then to 2050, implementation could continue at a comparable rate because new stuff will be cooked up by then, even though we don't know what it is yet. So I said at the beginning, no new invention is required. That's in the sense that we now can have clear line of sight to all the technologies needed, but not all of them are yet in the market. Sir?
Have you briefed this to Steve Chu yet? And
No.
If so, what did he say, or will you?
I haven't yet, because the chapters have undergone pretty intensive peer review. The whole book is out for peer review right now for another week. But I did talk to Anish in OSTP, and he asked me to brief John Holdren ASAP, and we'll figure that out over the next week or so. When we get more modeling results in, all the numbers will settle down enough. I gave you a little earlier preview than I normally would, being among friends, but I think Yeah, I know Steve pretty well, and I'm sure he will have time for this as soon as I'm ready, and it'll be sometime over the next couple of months.
Last question.
And, sir?
Yeah, thank you so much for speaking to us. I have a question around kind of the life cycle of replacing automobiles and replacing buildings versus upgrading existing buildings. I think your graph showed oil going to zero by 2050.
It's actually 0.06 million barrels a day because there's still some ancient gasoline-burning vehicles on the road that haven't quite retired yet, or they're run as antiques.
So is that about 2 life cycles? I think a car's like 7, 10 years.
Yeah,
or so.
yeah, and if you
And the buildings, what's the same assumption about replacing?
normal cycles. We're not accelerating in the buildings. We're somewhat we have an option of accelerated scrappage on the light-duty vehicles, but it's not essential to the result. The important thing in the autos is to head off a whole generation of inefficient oil-burning cars, EIA mobiles, that would otherwise be bought by getting down the cost curve and using Feebates together, and those drive each other, to get the revolutionary levels of vehicle fitness and the electrification that they allow on the market a generation sooner than would otherwise occur. Otherwise, you're stuck with way too much oil for way too long and way too much carbon for way too long, and the numbers don't work. But I think someone over here picked up earlier on one of the essential differences between this work and I think most others. Most others assume that such massive change must be driven by policy, compelling business to commit unnatural acts in the marketplace. We instead produce a powerful business logic and use policy to enable or unlock and sometimes to accelerate it. But it's a very light-handed policy using instruments that are almost not on the table at all. You know, like Feebates have been around since the 70s. Art and Dick Garwin and I separately came up with the idea. They only got adopted in late 2007 for the first time in France. There were a few little experiments, but kind of half-baked. Well, now that we know it works from European experience, what are we waiting for? It's a lot more powerful than either fuel taxes or CAFE standards, even though you keep the standards in a compatible way as a backstop against recidivism, but you'd want to make them irrelevant as quickly as possible. And we ran an industry charrette a few years ago on how to design Feebates to do that. So I think the notion of policy-enabled, policy-supported, but business-led logic is much better, because you can do all the policy stuff administratively or at a state level. No act of Congress is required, with a trivial exception about truck weight that's worth 250,000 barrels a day if you can do it. But I think doing an end run around Washington is a really good idea, because the gridlock does not look temporary. And when we published Winning the Oil Endgame in 2004, I did a courtesy pre-brief on the Hill, both houses, both sides, and the Republicans at that point controlled both houses. And when I was done, the most senior Republican Senate staffer said, "I'm really glad you're not coming up here to ask us to do something, because we would just screw it up." So I think that's probably even more true today, and therefore I think if I end up briefing this to Jeff Bingaman's committee, it would probably be, here are some wonderful federal policy opportunities for you that should have broad trans-ideological appeal and that conform to the objectives that both parties share, and it doesn't matter what your relative priorities are around national security, prosperity and jobs, climate and environment. We would do the same things anyway, so let's focus on outcomes, not motives. And if you choose not to take these opportunities for smart policy, don't worry, it'll be done at a lower level and your action will become unnecessary. And maybe you'll become unnecessary, I don't know, but they can draw that conclusion.
So with that, thank you very much, everyone.